All right, our next optimization problem. It says find the point on the curve y equals the square root of x that is the closest to the point 3, 0. For this problem, we are minimizing something. It says closest, and another way of thinking of that is minimizing the distance between 2 points. Now, this is another one where we want to sketch something. This involves a graph of the curve y equals square root of x. It would be helpful to sort of sketch that out to see if that points us in any particular direction. So we know that the square root function has a graph that looks kind of like that. And the point 3, 0 is on the x-axis. That's right there. Okay. Now, if I pick any arbitrary point on this curve, let's just put it right here. Okay. And let's give it an x-coordinate of just x. The y-coordinate of that point would be the square root of x, because that's the defining equation for this function. That means the point I'm looking at is x square root of x. Now, I can take the distance between these 2 points. It would be this line right here, okay? And we know that distance formula is a way of finding the distance between 2 points. Distance formula is the square root of the difference between the x-coordinates squared plus the difference between the y-coordinates squared. That's x minus 3 squared plus the square root of x minus 0 squared. Okay? Now this function, although I can work with this and it's not going to lead me astray or anything like that, the radical in here makes the derivative step just a little complicated. It's not the worst thing we've ever seen. We've dealt with much worse, but there is a way to make the work easier on you. And this is fairly typical when we do optimization problems involving distance formula. If I were to square both sides of this function and write this, d, capital D of x, is equal to, the squaring is just going to get rid of that radical, x minus 3 squared. And then if I square, first of all, the square root of x minus 0 is just the square root of x. Squaring that gives me just x, so that's a lot simpler. If I maximize or minimize this function, the value of x that does that, the value of x that minimizes or maximizes this, will be the exact same one that maximizes or minimizes this. And the reason for that is because the square root function is an increasing function. If I can find the radicand in here, which is the thing inside the radical, and if I can find a value of x that maximizes that, then I'll also be maximizing the square root of that number. Okay, so you don't have to do this, but it's going to make the work significantly easier. Maximizing this function or minimizing this function will give me the same results as far as the x value is concerned of maximizing or minimizing this function. So is there any constraints that we have to worry about? Well, for this one, the function is going to be defined on the interval from 0 to infinity, because that's where the square root function is defined. And remember, x represents a value in the domain of our square root function because it's giving me a point on that curve. So this is not a closed interval by any means, but I do have one endpoint. I have 0, and it's actually really easy to see how far the point 0, 0 is from the point 3, 0. It's 3 units away, okay? But let's not get ahead of ourselves. I want to start by looking for relative extrema in this function. Once again, I need to take a derivative. Capital D prime of x would be 2 times x minus 3, using my chain rule here, plus 1, which is equal to 2x minus 6 plus 1, so that'd be minus 5. And if we set that equal to 0, that implies that x is equal to 5 halves. Solving that gives me x equals 5 halves. Okay. Now, what is the type of relative extreme that we're looking at? Is this a maximum or a minimum? And this is one case where I absolutely would have no problem using one of the derivative tests. The second derivative test makes this really easy. I'll let you do that. The second derivative of this would just be 2. So what does your second derivative test tell you? But I want to think of this one in more logical terms as well. This number here has to be either a relative maximum or a relative minimum. It's definitely not a relative maximum. The reason I know that is because I can keep this point moving along this curve, and I can make it arbitrarily far away from this point, which means this distance can be as large as I want to make it by just moving this x further and further to the right. So there is no maximum for this function, for this guy. It can be made as big as I want to make it. But it does make sense for there to be a minimum, a smallest value. And logically, that would be what we just found. So again, you can use your second derivative test, but with that rationalizing it, with that thinking through, it makes sense that we have just found the point, the x value of the point that gives us that minimum. Now it says find the point on the curve, so I need a y coordinate as well. But remember, the y coordinate is just the square root of the x coordinate. And so that would be it right there. It did not ask me for what the distance was, so I don't need to plug anything back into my distance function now. I'm done at this point. Okay? All right. So, let's move on. This one is a little bit more involved, and it's going to involve some geometry. Optimization problems a lot of the time will involve some geometry. We've already done a little bit with a volume formula. Here it says that we have a right circular cylinder which is inscribed in a cone with a height of h and a radius of r. And what we want to do is find the largest possible volume of such a cylinder. So we have a cone, something like this. Drawing a diagram. This is definitely a problem where you have to draw a diagram. Okay? And then we're inscribing a circular cylinder inside here. So let's say it looks something like this. Something like that. Okay? Now notice there are different sizes of circular cylinders I could inscribe in this thing, because I can make the radius of the cylinder smaller, which will actually make this cylinder taller. So as I decrease one dimension of the cylinder, the other dimension is getting bigger. And so again, we're sort of playing that balancing act. How does that affect the volume of that cylinder? By the same token, if I make the radius of this cylinder larger, then where this is going to hit the cone would have to be at a shorter height than it is now. So that would, as radius of the cylinder increases, the height would decrease. We want to find exactly what the largest possible cylinder of under this constraint could be. And notice we're not given numerical values for the dimensions of the cone. We're given letters. So we're told that the cone has a height of h and has a radius of, r, lowercase r. Okay? These are to be treated as constants, because the size of the cone is not something that we're able to change. The size of the cylinder is something that we're able to change. So even though we're using letters, you need to be thinking of those letters as constants. Okay? Now, we want to find some sort of relationship between the dimensions of this cylinder and the dimensions of this cone. So what I'm going to do is put an altitude into this cone and sort of take a little right triangular slice out of it. Okay? And notice that the cylinder is also going to make a right triangle. So I'm going to take this right triangle and this other right triangle inside of it and kind of move it outside the picture right here. Okay? So this leg would represent the height of our cone. That would mean it's equal to h. And make a right triangle. There's also this side of the cylinder that would come in there. I'm going to put that here to indicate the side of that cylinder. Okay? Now, the base of this larger right triangle is the radius of the cone. It's lowercase r. Okay? And what I want to do is identify some variables here. So I'm going to let capital R be the radius of the cylinder. And I'm going to let capital H be the height of the cylinder. Okay, since we're looking at two different figures here, each with their own radius and height, it can be a little bit confusing if I'm calling both of them R, both of them H. So I'm using a capital for one, lowercase for the other. Okay, this thing right here would be capital R. All right, because that would correspond to the radius of my cylinder, which means this little piece right here would be little r minus big R, because it's this larger piece minus this smaller piece. Finally, that would be capital H right there, because that would be the height of my cylinder. So now that I've found all of these values here, how can I relate things? Well, both of these right triangles have two angles in common. They both have right angles, and they both share this angle. If you have two triangles that have two pairs of congruent angles, from geometry we know that those two triangles are similar. And with similar triangles, we can set their side lengths up in proportion to each other. So what would such a proportion look like in this case? If I take the height of the larger right triangle and put it over the base of the larger right triangle, so that would be little h over little r. And then if I can set that equal to the height of the smaller right triangle, which is capital H, over the base of that smaller right triangle, which is little r minus big R. This is a proportion that would be true because of those similar right triangles that I have right there. Okay, and what I'm going to do here, because ultimately the goal is to make a substitution. Both capital H and capital R are unknowns. Remember, little h and little r are constants. We're not treating them as unknowns. Right now, on the right-hand side, I have an expression involving two unknowns. I'd like to solve for one of them so that I can make a substitution somewhere in an upcoming step. So I'm going to solve for capital H by multiplying both sides by little r minus big R. That's going to equal h over r times little r minus big R. Okay? Now what do we need to do? Well, what we're trying to maximize is the volume of that cylinder. And the cylinder, the volume formula for that cylinder is pi r squared h. That's the volume for any cylinder. In this case, though, that would look like pi big R squared big H, because that's the radius and height of our cylinder. And this is where we have two unknowns where we really just want one. But this is the constraint that I'm working with. So I want to make a substitution. I want to substitute this expression for the capital H right here, which gives me pi r squared times little h over little r times little r minus big R. Okay? And then what I'm going to do a little bit of rearranging. I'm going to write this slightly differently. Pi is a constant, h is a constant, r is a constant. Let's move all of our constants out here. So that would be like pi h over r. And then I'm going to take this r squared and multiply it into those parentheses. That's going to be little r times capital R squared minus r cubed. Okay? I'm doing that because that's going to help me when I take my derivative. Okay. Are there any constraints that we need to worry about on this function, by the way? Right now I'm looking at a function of capital R, because capital R is the only unknown here. All of the other letters are constants. So is there any kind of constraint on capital R? Well, it has to be bigger than 0, because if it were 0, then this thing would shrink down to a flat circle, which is not a cylinder. Obviously, it can't be negative. You can't have a negative radius, so it has to be positive, greater than 0. It also has to be strictly less than little r. Sorry, I said if big R was equal to 0, it would shrink down to a circle. It's not a circle. It would shrink down to a line right here. If I let big R equal little r, that means that the base of this cylinder is going to be exactly the same as the base of this cone, but then this thing would end up having no height, and again, not a cylinder. So once again, my capital R is restricted to an open interval. I don't need to check endpoints, but I do need to find relative extrema. So I'm going to take a derivative. I'm going to differentiate V with respect to big R. Remember, pi h over r is a constant, and so from the constant multiple rule for derivatives, that stays put. What's the derivative of this inside part look like? This is going to be 2 little r big R minus 3 big R squared. And we set that equal to 0 to find critical numbers. Okay, let's factor that. Pi h over r. I can pull a big R out of that, leaving me with 2 little r minus 3 capital R equals 0. Remember, capital R is the unknown here. So from this factor, R could equal 0. From this factor, if I set this equal to 0 and solve it, I'm going to get capital R equals 2 little r over 3. So that's 2 little r over 3. Okay? Now again, 0 is not in the domain of our function, so we can throw that one out. 2r over 3, which is the same thing as 2/3 times r, would be between 0 and r. So this is a usable one. All right? Now, I want to determine if this value for capital R gives me a maximum or a minimum. Let's use our second derivative test here. Second derivative is going to look like this. Pi h over r. And then I'm going to differentiate this guy. So if I do that, I'm going to end up with 2 little r minus 6 capital R. All right, and I want to evaluate that at my critical number, which is 2 little r over 3. That would be this. Pi h over little r times 2 little r minus, so 6 times r, think of this as a 2/3. 2/3 times 6 would be 4. Okay? This is equal to negative 2r. The r here can cancel with that, so I end up with negative 2 pi h. H has to be positive because of the constraints in this problem. Pi is positive, negative 2 is negative, so we definitely have something that's less than 0 here, which means this guy is concave down, giving us a maximum. That verifies that this value here gives us a maximum. So the last thing that we need to do is find the actual volume that constitutes that largest volume. So what I'm going to do is go back to my original volume formula, which we wrote in this expression right here. V evaluated at r equals 2r over 3 is going to equal pi